Hello, I am Riccardo Martoglia and I present a paper towards multimodal big data road traffic forecast at different time aggregations and forecast horizons. So first of all, the motivations of the research. We are in a smart city context, and in particular, in this context, research can lead to significant improvements to public services. And when we talk about traffic forecast, it is particularly useful in intelligent transportation systems, reduction of urban pollution, public service transport, and all this research can improve citizen well-being. However, there are various factors that are not sufficiently investigated in current traffic forecast research, in particular forecast horizon, data granularity, traffic condition, and how all these variables interact between themselves. So, our paper contribution, this is a work in progress. A short paper will present a novel approach which integrates both statistical, classical statistical models and also machine learning methods within the Apache Spark big data infrastructure. And so we are able to use jointly the Spark mlib, and we show decision tree, in particular the decision tree model, and also Spark Panda function API, which allows us to exploit the classic ARIMA model. We present some preliminary tests on our platform in a real use case. The real use case is the MASA, Modena Automotive Smart Area, which is an area of Modena which is equipped with smart cameras and sensors. And we perform some preliminary tests and we analyze the accuracy by considering different data aggregation level, traffic density level, and also different time horizons, as we will see. Let's start with a brief panorama of the state of the art. You will find in the paper all the discussion, of course. Anyway, there are several works on road traffic prediction. In particular, there are several papers which consider classic statistical methodologies such as ARIMA, GARC, and so on. And these papers are not specifically supporting a big data context. There are also some other papers which exploit machine learning models, for instance in Apache Spark, but they do not consider classic statistical forecast methods. So there is a lack of big data approaches supporting big data platforms, which are able to provide and exploit both machine learning method and classic statistical methods. Many researchers try to understand how different factors affect the forecast. For instance, there are papers working on atmospheric condition or road indicators and so on, but few work focus on the concept of data granularity and time horizon. So let's give an overview of our approach. Our approach is a data management architecture we built and which derived from the European class project. The architecture is based on Spark, and in particular on the Spark structured streaming for real-time streaming data management and storing and analysis. And we built this architecture and we make it work for hierarchical aggregation in real time, and in particular the incoming data is in real time aggregated at 1 minute, 15 minutes and 1 hour step aggregations, and we have all these different aggregated data available in the system. Then there are the two different data management paths we consider in this paper for analyzing and performing the forecast, the prediction, the traffic prediction. The first path is the MLlib path, which enables us to work on the machine learning model, and the second path is the Pandas function API, which enables us to exploit the classic models, the classic statistical models, also in a big data context, which is seldom used and seldom available in current research. Just some more details about the two different paths. For MLlib, we support the different machine learning models. In this paper, we focus on the decision tree model, and in this path, machine learning model jobs are submitted one at a time, and they can potentially work on very, very large time series, so we can exploit this path for very long time series. But we have also the Pandas function API integration in Spark. We work on it, and we are able to support in this way also the classic statistical models, and in this paper we focus on ARIMA in particular. So let's have a look at the data processing, how data processing is performed in our system. So let's analyze the data management pipeline, the data processing pipeline we propose in this approach. There are different steps, and we will have a short description of each of them. The first steps are pre-processing steps and are in common between our two approaches, the MLlib approach and the Pandas function API approach. The first step is data resampling, which is performed in order to get equally spaced observations in relation to the data granularity level. The second step is the null values management, where we associate zero values to null observation in order to handle no vehicle flow situation, and in particular feed forward or interpolation are not the correct way to model and to solve this problem, so we handle it in this way. The third step is the time extraction, where time information, hour, and also date such as weekend and so on is extracted and used as additional feature for forecasting model. And then there are the subsequent steps which are needed, in particular for the MLlib pipeline in the upper part of our graph or in the Pandas function APIs. For MLlib path, we need lag extraction to obtain lag values for each observation, and vector assembly to create a single vector containing all the extracted feature. While for the Pandas, we need logarithmic transformation, which is performed through the Pandas module. So let's see the experimental evaluation we performed on our models. The experimental evaluation is performed in a scenario where we have over 500 different map points, and so over 500 different time series. Each time series has 7 days duration, and we have it in different granularities, in particular 1 minute, 15 minutes, and 1 hour granularities, which are always available in real time in our system. We analyze these time series and group them in two groups which are representative, one for high traffic density and the other for low traffic densities. The models we consider are the decision tree, as we said, which is representative of the MLlib path, machine learning lib path for Spark. The features are lag values, hour, and weekend information. The training and test split is performed on a 80-20 ratio. As for the classic model, we consider ARIMA, as we said, and we perform in this context a classic cross-validation on a rolling basis, so to respect the temporal dependency between the observations. The considered accuracy metric is the mean absolute percentage error. So let's consider some of the questions we want to answer. In particular, let's consider one-step forecast and the time granularity impact. The question is, are next hour predictions more accurate than next minute or next 15 minutes one, for instance? Let's consider the results. We see the results in the graph, and in particular we see that the use of a finer granularity in our test leads to a decrease in the error, as we also were expecting. And also we see that ARIMA seems to get a higher accuracy value compared to decision tree. We also made some further tests to answer different questions, such as how does forecast accuracy vary in relation to traffic density, and so the impact of traffic density on the forecast. These are the results we obtain. On the left we have the low traffic conditions, and on the right we have high traffic condition. We can see that we have lower error when the traffic density is high. This is because we think roads are more congested, and so data is possibly less subject to random fluctuations. We analyzed it in this way. As to the two traffic level, we see that the behavior is in line with the one we shown in the previous test, in particular with respect to the different data granularities. Let's consider also the situation of the n-step forecast, and in particular let's try to answer some more complex questions on the influence of the time horizon, the impact of time horizon on the prediction. In particular, we see how does time horizon impact in forecast accuracy. In particular, we try to predict the next 1 or 3 or 6 hour average traffic density in this test and see what is the obtained accuracy. And also fix a forecast time horizon, which data granularity should be used to get the lowest error. Of course, these are preliminary tests, but we have some initial consideration on it. These are the results we present in the paper. We can see, as to the first question, that the ARIMA model, and we see that the increase of the time horizon leads to a consequent increase in the forecast error, as expected, we should say. But also let's consider the second question, which is a more complex situation. We can see that as to data aggregation, each data aggregation requires a specific n-step forecast. In particular, for very fine aggregation, we need a high number of steps of which we perform the average. So to predict the average next hour, and so to consider in shorter horizon, we see that in our test, finer data granularity leads to better accuracy, as we see on the graphs. As to predicting average next 6 hours, so longer horizons, we have that coarser granularity level, and so lower number of steps in the forecast is better, seems to be preferable. We also have some brief notes on the efficiency evaluation, which however is not the current focus of the research anyway. We can see that comparing the execution time between our approach, the Spark Pandas function API configuration for ARIMA, and the standard Pandas execution, we can see that our approach is faster, and so this justify our architectural choice, not only for enabling a machine learning model, which in Pandas are not available, but also for an efficiency point of view. And we can also see that when we consider machine learning models such as decision tree is particularly efficient, is more efficient than classic models, and this makes us confident that future parallel optimized execution will enable a very high number of predictions to be made in real time. So we proposed a novel approach for traffic forecast. In particular, the approach integrates both classic and machine learning models in a Spark-based big data architecture. And from the preliminary test, we saw that we tried to understand the impact of different variables and to answer some questions which are not often considered together in the available state of the art. In the future, we plan to continue the development and testing of our approach, and we will consider further models to integrate and also further data scenarios, and we also will improve the current models with additional techniques such as grid search, outlier detection, and so on. We hope that these techniques will help in improving the smart cities scenario and for improving citizen well-being, because we hope that these techniques will become the basis for supporting more complex tasks such as public transportation logistics or road trip optimization, decision support for reducing air pollution, and so on. Thank you very much.